In the previous class, we are discussing about the properties of elements of 16th group. Now we can discuss about that the compounds and the elements of 16th group. So first we'll discuss about the oxygen. So let us write that how the oxygen is prepared, what are the properties of oxygen. We know that how we get the preparation of oxygen by the decomposition of oxides, or we can write that from different compounds or fractional distillation of air. Then we can write that it is that we'll say that it is we'll write that that is oxygen we are going to discuss is, so that is we'll write that the oxygen, or it is also called as dioxygen atom. So it is dioxygen or oxygen. We used to say that oxygen, if we say that it is like this, then let us check then what is the preparation methods of oxygen is. So the preparation methods what we used to write is, that is first we can discuss about the lab preparation methods. So what is the laboratory preparation methods? I can say that it is the lab preparation methods. So lab method is, that is by the decomposition of KClO3. So lab method for the preparation is by the decomposition of KClO3. When it gets decomposed, it gets converted into that KCl plus O2 is liberated. So if we write that, it is like this. We are going to write it as like this, that is twice, and we'll get that oxygen as like this. So this is the lab method for the preparation of that is oxygen. And the rate of reaction increases in presence of catalyst, that is MnO2, because in presence of MnO2 the reaction goes for completion. So that is the laboratory method for the preparation of oxygen is. Now we can write that the preparation of oxygen by decomposition of certain compounds or oxides. We can also say that by thermal decomposition of, so we can write that by thermal decomposition of, that is, we can say that by thermal decomposition of, we can say that the oxides, the decomposition methods, we are going to write that. So by thermal decomposition of, if I'm having silver oxide, because we can write that the silver oxide, when it decomposes, it will get converted into the silver plus oxygen is liberated. Then we can write that the decomposition of mercuric oxide, that is O2, that will decompose to give you the mercury plus half O2. We can write that. Similarly, you can write that the decomposition of that is the lead oxide, because the Pb3O4 or PbO2, due to the inert pair effect, the PbO is more stable in that is in +2 state. The lead is more stable. So we used to write that it is like this, that is when Pb3O4 is heated, it will get converted into the PbO, plus we get that it is the O2 which is liberated in the reaction. So I'm going to write this as, that is the thrice of PbO plus I'll get that the oxygen is liberated like this. Or even you can write that if it is PbO2, then also it will get decomposed to get converted into the PbO, plus we'll get that half O2 in the reaction. Like that we can write that the decomposition reactions of different oxide is. So the different oxides, we can write that the metal oxide, we have written that even the oxide, that is decomposition of H2O2. So we can write that that is decomposition of H2O2 when it gets decomposed in presence of that is, you can write that MnO2, then it will get converted into H2O plus that is O2 is also liberated in this reaction. So the decomposition, these are the decomposition reactions of different compound in which the oxygen is liberated, and the oxygen is prepared in these reactions. Even we can write that the decomposition, the other decomposition of the compounds now we are talking about, that is H2O2, the decomposition of KMnO4, the decomposition of K2Cr2O7, all these liberate oxygen on their decomposition. So I'll write that the decomposition of, I'll write that is K2Cr2O7, that when it gets decomposed, it is going to convert it into, that is potassium chromate, then we'll write that K2Cr4 plus Cr2O3 plus O2, that is the product of the reaction, we can say that. So if I write that it is like this, that is 4, that is we can write that it is so I'll get this as twice, and we get that oxygen is liberated in this reaction. So that is how we are able to write the oxygen in this case. So even we get that like this. Similarly, I can write that that is again the decomposition of KMnO4. When KMnO4 is decomposed at high temperature, what we get is it will get converted into MnO2 because as this converts into that is K2CrO4, that is a chromate, similar chromate, and that is the chromium oxide. Similarly, potassium that is permanganate decomposed to give you that is green color compound K2MnO4 plus MnO2. We used to say that, and we get that it is the oxygen which is liberated in the reaction. So you can write that it is like this. So that is how we get that oxygen in the reaction is. So that is how we get that when it is heated, it will show the decomposition reaction. All are the decomposition reaction which take place on heating. So these are the decomposition reaction by which we get the oxygen. So in all these cases, the oxygen is liberated as a gas. Oxygen is liberated as a gas. This is by the thermal decomposition. Now we can write that the commercial preparation of. So commercially it is prepared by preparation is it is prepared by the fractional distillation of air. So commercially it is prepared by the fractional distillation of air. We used to say that prepared by the fractional distillation of air, that is the nitrogen is removed and the oxygen is removed. Fractional distillation of that is air by removing CO2 and H2O from the air also. So distillation of air mixture, that is so it is by fractional distillation of air. What we used to say that after removing we used to say that is removing CO2 and H2O, because the boiling point and the freezing point of O2 is known to us. That is we used to say that the boiling point is 90, whereas freezing point is 55 Kelvin. So the boiling point of O2 is that is 90 Kelvin, and the freezing point of that is we used to say that the freezing point of O2 is 55 Kelvin. So we used to say that can be easily fractional distillated. So that is how we can prepare the oxygen by the fractional distillation of oxygen from the air after removing the CO2 and H2O. So this is the method, these are the methods by which we can prepare the oxygen by decomposition of the compounds, or in the lab method by the decomposition of KClO3. So these are the method for the preparation of oxygen, and commercially it is prepared from the air because air contains that oxygen 20% by volume. So it can be fractional distillated. Next we can write that the properties of oxygen. So if we discuss about the properties of oxygen, we can write like this. The properties of oxygen is, the properties of oxygen we can discuss that is already the boiling point and freezing point as a property is known to us. Now we can write that it has 3 stable isotopes. So if we write this as it has 3 stable isotopes. So stable isotopes, that is we say that oxygen 16, oxygen 17 and oxygen 18. So these are the 3 stable isotopes of oxygen is. So molecular form, the molecular form of O2, the molecular O2 is, we say that O2 exists as a molecule O2. So it exists as in molecular form of O2, that is molecular form of O2, which is paramagnetic in nature, even though it has an even number of electrons, which is paramagnetic is nature, paramagnetic in nature, even it has even number of molecules. So right, even with 16 electrons, you can say that. So paramagnetic in nature, which can be calculated by, it is calculated by molecular orbital theory. We know that, calculated by molecular orbital theory. So molecular orbital theory, we know that it is in the anti-bonded electrons, the 2 unpaired electron in the pi star 2px and pi star 2py. Molecular orbital theory, which can be proved by that. So that is how we can write that, how it exists. What are the isotopes? It is paramagnetic in nature. The reason is known to us. So that is how we can write that. O2, we can say that now. it reacts directly with most of the metal and non-metals. So it reacts directly with most of the metals and non-metals. With most of metals, except we can write that it is we'll say that gold, silver, platinum, like that. No? The inert metal these are, and non-metals. So and non-metals it reacts directly. So we can write that like this. That is, suppose we are having that is the calcium, aluminium, phosphorus, like that. So the calcium when reacts with O2, it converts into calcium oxide. When we can write that aluminium reacts with O2, it forms aluminium oxide, Al2O3. When phosphorus reacts with O2, it converts into that is P4O10. Depending on the amount of oxygen, this and this can be formed easily. Depending on the amount, P2O3, P2O5 or P2O3 we can write like this, P2O6 we can write like this. So depending on the amount, we are able to write that which will be formed, P4O10 or P2O6, depending on the amount of oxygen. Even it reacts with carbon to form that is carbon dioxide. We can say that carbon plus O2 gives you carbon dioxide, and we can write that carbon dioxide. Then few sulfides also react. ZnS plus O2 will convert into ZnO plus SO2, that is the oxide it converts that zinc into the oxides, and we'll write that it is we'll say that copper, if we take that the CH4, the combustion reactions also Cu plus, then similarly reaction I have told you that, as I have told you that sulfides, no? So it can be the lead sulfide or copper sulfide also, like that we can write that. So CH4 on combustion will get converted into the CO2 plus H2O, that is twice of H2O, so we'll get that like this. So these all are the combustion type reactions. So all can be called as the combustion type reaction. In all the cases what we used to write is they all are exothermic reactions. These all are exothermic reactions. So since they are exothermic reactions, they can take place very easily. Exothermic reactions, and that is because of the bond energy. Because of the bond energy of O2. So we can write that because the bond energy of O2, that is bond energy of O2 that is only 431 kilojoules per mole. That is not very high. So it is around 431 kilojoules per mole. That's why we used to say that it is going to show the reaction like that. So it is 431, or it is around you can write that, because exactly it is 493. So we can write that around exactly it is 493 kilojoules, which is much less than nitrogen. Nitrogen is 945 kilojoules per mole. So 945 kilojoules per mole, it is very, very high. That's why we say that nitrogen is an inert gas, but not oxygen. Oxygen cannot be called as an inert gas. The reason is because its bond energy is very less. So it's directly react with most of the metals and non-metals, because all the reaction what we are going to write, these are the exothermic reactions. So the reaction can take place very easily. Some of the catalyzed reactions are there. So we can write that some of the catalyzed reaction. So some of the catalyzed reaction of oxygen. Some of the catalyzed reactions of oxygen are we can say that is like this. When SO2 reacts with oxygen in presence of vanadium pentoxides, in presence of V2O5, that is in presence of V2O5, it gets converted into that SO3. So this is the reaction with the catalyst is. And if we write that HCl when treated with, also we can write that when HCl is treated with O2, it gets converted into the Cl2 plus H2O is formed in the reactions. So we can write this as like this. That is the reaction is like this. That is forming that is HCl. The excess of HCl react with oxygen to form. That is like this. So that is also a catalyzed reaction in presence of CuCl2. This is in presence of vanadium pentoxides. So these are the reaction which take place in presence of catalyst of oxygen with some of the compounds, that is SO2 or HCl. Like that the product of the reaction is. Now, if we use that, if we write that, what are the uses of oxygen is? So the oxygen uses, we know that the diluted oxygen is the diluted oxygen with helium and that is with the neon. They are used for artificial respiration. Oxygen is very important for combustion. We know that. So if we write the uses of oxygen, we can write that. That is, so we can write that. What are the uses of oxygen? So I can write that. That is first we can write that. O2 plus hydrazine, that is N2H4, the mixture. So mixture is used as a rocket fuels. So that is used as rocket fuels. Then we used to write that a mixture of, that is the mixture of, that is, you can say diluted oxygen. Not, it is not a mixture, I have to say that. The diluted oxygen. So diluted oxygen with helium, that is oxygen with helium, we used to say that, with helium and right now generally it is helium. So diluted oxygen with helium is used for artificial respiration, we used to say that. So artificial respiration, we used to write that, that is artificial respiration, that is how we can write that. So that is artificial respiration. So these are the uses, very important uses of oxygen are these only. So these are the important uses of oxygen, we can say is. Now oxygen exists as oxides. The simple oxide, the mixed oxides, we used to write that. So let us write that the oxides formation. So we used to write that the oxides are. So I'm going to write that, we'll write the oxides. So we'll write that what are oxides? The oxides will be the mixed oxide and the simple oxides. So I'm going to write that the simple oxides and the mixed oxides. So we can write that it is, we can write that next point, we can write that this is uses, then we'll write that oxides. So oxides are of two types. One is called the simple oxides and the mixed oxides. The simple oxide and the mixed oxides are like this. The mixed oxides. So the simple oxide means we'll have calcium oxide, we'll have lithium oxide, we have magnesium oxide, etc. We can write that these are called simple oxides. That is Al2O3, that is P2O5, that is called the right? The simple oxides. The mixed oxides are, we'll write that it is Fe3O4. It is called the mixed oxide because it is a mixture of this and this, Fe2O3. So this is called the mixed oxides. It is a mixture of Fe2O3. So that is a mixed oxide. Similarly, I can write that the lead oxide is a mixed oxide as like this. The Mn3O4 is a mixed oxide. We used to write like this. So these are few examples of, we used to say that the mixed oxides are. So these are the, we'll say that the mixed oxides, etc. We can say that. So that is the mixed oxide. We can write in this manner only all these oxides. Now we write that the acidic oxides. If I write acidic oxides, the basic oxides, and the amphoteric oxides. So amphoteric oxides. So let us write that what are, right? So acidic oxides are generally formed by non-metals. So generally formed by non-metals. Formed by non-metals, we used to say that. And the oxide, basic oxides are generally formed by metals. Amphoteric oxide, that depends on the nature of metal, like we'll check that part. But here I can write that, for example, I can write that CO2, SO2. I can write that it is SO3. Then I can write that it is NO2. Then we can write that it is, right, NO2. They are acidic oxides. Then we can write that B2O3, that is acidic oxide. Then P2O5, P4O10, O10, N2O5, that is the acidic oxide. That is Cl2O7, they are acidic oxides, etc. we can write. So all the oxides what we are going to form by the non-metals, they are, we say that it is acidic oxides. The metal oxides, we can write that all metal oxides, that is lithium oxide, we can write that it is a metallic oxide. We can write that MgO, that is we'll write that calcium oxide, strontium oxide, barium oxide, etc. I can write that. You can write that metal oxides are basic in nature. So you can write that TlO2, Tl2O3, that is Bi2O3, that is etc. We can write that. The metal oxides are basic in nature. The amphoteric oxides are, we can write that the amphoteric oxide, that is beryllium oxide, we can write that. Then we can write that aluminium oxide, that is amphoteric, zinc oxide, it is amphoteric, SNO is amphoteric, PbO is amphoteric. We used to write that MnO2 is amphoteric. Then we write that that is the amphoteric ones, which act as acid as in presence of base and base as in presence of acids. So I can write that it is GeO2, the germanium oxide, that is Cu2O, and then I write that CrO2, etc. These are the some of the, we have written that they are amphoteric oxides. So these are what we called as the amphoteric oxides are. Now we can write that, etc. We can say that the neutral oxides are, the neutral oxides we used to write that, the neutral oxides. The neutral oxides are, we used to write that, that is NO, N2O, then it is CO, and these all are gases. These are gases, the neutral oxides, they are gases, but H2O is also a neutral oxide, but it is a liquid. So these are the neutral oxides, what we used to say that. Now if we write that, the nature of oxide in the periodic table. So if I discuss some part for the nature of oxides, we can say that in periodic table, the nature of oxides in a group from top to bottom, the basic character increases. From LHS to RHS in a period, then we say that the acidic character of oxide increases. So we say that the nature of oxides. So nature of oxides. In a group from top to bottom, the basic character increases. In a group from top to bottom, the basic character increases. Basic character of oxide increases. Character of oxides increases. Whereas in a period, we'll say that, whereas this is increases, whereas in a period, we used to say that in a period, we'll say that from LHS to RHS, LHS to RHS, the acidic character, we used to say that, the acidic character of oxide increases. So the acidic character increases. That's why we'll say that, for example, I can write that, for example, I can say that, that is B2O3 is more acidic than CO2. That is more acidic than, I can write that, that is N2O5, that is more acidic than P2O5. That is more acidic than, I can write that it is P2O5. Then I can write that this is more acidic than SO3. It is more acidic than, no, I have written like that. The acidic character, I will write like this, that is what we have to write as Cl2O7, because I have written like this. This is the, we can write that. The acidic strength is, according to the sentence what we have written as. So the element which is present on the extreme left, it will have a more acidic character, because from LHS to RHS, the acidic character of oxide increases. So that is what I have written, right? The acidic character of oxide increases. So it is like this. That is the nature of oxide is. So this is the nature of oxide is. That is how we can write the nature of oxides. Now we can discuss that. We can say that if in a particular element, as the percentage of oxide increases, its acidic strength increases. So for an element, for elemental oxides, for element oxides, we can say that oxide, the acidic strength of oxides increases. Acidic strength of oxide increases. Oxide increases as the, we'll say that as the percentage of oxygen increases. As the percentage of oxygen increases. Of oxygen increases. So let us check that how we are going to write that. The acidic strength is. So I'll write that. Suppose we write talking about the element. If I write that MnO, that is, I'm going to write that some of the compound of that Mn2O3, then it is MnO2, then I'm going to write that it is Mn2O5. You can write that Mn2O7 like that. So Mn2O5, Mn2O6 and Mn2O7. So O6 and Mn2O7 we can write like this. So these are the oxides I've written. Now we'll say that these two are acidic in nature and this is amphoteric and these are basic in nature. So you can say that as the percentage of oxygen increases in the oxides, they are acidic nature, then it is amphoteric, that is MnO2. We have already written that MnO2 is acidic, that is amphoteric. Then we get the basic nature. Because the percentage of oxygen increases, then its acidic character increases. Written that wrong. So if the percentage increases, then its acidic character increases. So I'll write that. This is more acidic and this is basic. If the percentage of oxygen is less, then it is basic in nature. If the percentage of oxygen is more, it will be acidic in nature. You can write the example like this. So that is how we are able to predict that as the percentage of oxygen increases, the acidic strength of oxide increases. So it increases as the percentage of oxygen increases in the reaction. So that is about the oxides, we can say that. Now the oxide which shows the acidic as well as basic nature. I'm talking about amphoteric oxide. They react with acid as well as base both. So the amphoteric oxides reacts with acid as well as both base. The amphoteric oxides reacts with acid as well as base. With acid as well as base. So you can take one example, that is, suppose I'm talking about SnO reacts with NaOH, then I'm going to write this as, that is NaSnO2 plus H2, you can write that. So you can write NaSnO2 plus H2 is liberated in that. That is how we can write that. So in this case, you can write that this is sodium stannite. Sodium stannite. Right? And if I write like this, that is SnO2 plus NaOH, then in that case, I'm going to write that it is Na2SnO3. Then in that case, this is sodium stannate. Sodium stannate. This is sodium stannate, and again in this, the hydrogen is liberated. So like that, we are able to write the reaction of, we can say that it is the reaction of NaOH with the amphoteric oxide. Similarly, I can write that also with the reaction with the base, that is SnO reacts with the HCl, that is reaction with the base. It is the reaction with the acids. I'm going to write that. It is like this. So this is SnO3. We get that twice. So we can write that in this case it will be H2O. That will be formed with the reaction. Here we can write that it is HCl, so I'm going to write that SnCl2 plus H2O, we get that. And if it is SnO2, we are going to write that HCl, then we get that the reaction as SnCl4 plus H2O, we are going to write that. This is how we are going to write the reactions of, that is, amphoteric oxide. So these are the oxides what we have to discuss is, and that is about the oxides what we should know. So these are the oxides what we have. The acidic oxide formed by non-metals, the basic oxide and the amphoteric oxides, as well as the neutral oxides. So these are the type of oxides what we have discussed. Yes. This is all about the oxides, the information which is required about the oxides. There is, we have discussed this information in periodic table also about the oxides. We have discussed the same information in periodic table about the oxide is. So that is how we can write that. Next I can write is, that is ozone. It is the allotrope of oxygen. So I'm going to discuss that about ozone, that is O3. It is an allotrope of oxygen. So it is allotrope of O2. So ozone is allotrope of O2, and ozone is a very strong oxidizing agent because it is oxidized oxygen. So it will be a strong oxidizing agent. So it is highly reactive. So it is highly reactive, and it is formed from oxygen. It is present in the atmosphere. That is around 20 kilometers from the earth crust. That is around, we can say that 20 kilometers from the earth crust. 20 kilometers from earth crust. There is a layer of ozone which is present there. So from earth crust, it protects us from the UV radiations the UV radiation which are coming out from the sun rays. So it protects us from the UV radiations, right? So it protects us, the layer which is present, the ozone layer which is present around in the atmosphere, that is around 20 kilometers from the earth crust, that protect us from the UV radiations, because UV radiation cannot enter that ozone layer. So the radiation cannot pass through ozone layer. Pass through O3 layer. That is the ozone layer, we used to say that. So that is the ozone, the importance, and we have seen that what is that? It is highly reactive because it is an oxidizing agent. So obviously it will be reactive. Now let us check that how we can prepare that. So we'll write the preparation of the ozone. So if I write the preparation of ozone, obviously the preparation of ozone will be from oxygen. So the best method for the preparation of ozone is from oxygen with a silent discharge tube. So we'll write that that is ozone when treated with, so O2 when that is anhydrous. So the anhydrous O2 when it is right now silent electric discharge. Because this silent electric discharge is required. Otherwise, if we heat that, then ozone which is formed may get decomposed. So that's why in silent electric discharge it will not get decomposed. So silent electric discharge will get converted into, that is O2. So it is that what we get. So it will convert into that, the O2 will get converted into the ozone. So that is the method of preparation of ozone. Now what we have in this case is the ozone which is formed is around 10% in this. It is only 10% which is present in this. And the delta H of reaction is not very high, but it is positive, that is 142 kilojoules per mole. So obviously it is an endothermic reaction. That's why we require the silent discharge for the reaction is. So, and we know that it is that is endothermic process. So we require that silent discharge. So we can write that it is endothermic reactions. So endothermic reaction. So a silent electric discharge is required. Endothermic reaction. So a silent electric discharge is required. Silent electric discharge is required, and it prevents the decomposition of ozone also. And it prevents the decomposition of ozone. So it prevents the decomposition of ozone. So decomposition of ozone, we will say that. So it prevents the decomposition of ozone. What we write that is, it is like this. So That's why the silent discharge is required. So that is about the requirement of silent discharge. Now what happens if the concentration of O3 in that is concentration of O3 is greater than 10%. Then as it is highly reactive, so if the concentration is is greater than 10%, then it requires the special containers to store them. Because if the percentage is high, its concentration is high, then it is highly reactive. So it requires special containers to store them. So it is stored in a battery of ozonizers. Then it is stored in the battery of ozonizers. We say that battery of ozonizers. That is, it is stored in the battery of ozonizers, and pure ozone, that is the pure ozone, we say that, and the pure ozone that is having a melting point. We can say that because it is a gas. So let us discuss only the boiling points. The boiling point of around 350, we say that 385 Kelvin. So it is 385 Kelvin. It has a boiling point of around 385 Kelvin. So the pure ozone, which is having a boiling point of 385 Kelvin, can be condensed in the vessel. So can be condensed in the vessel. So condensed in the vessel. So it will be condensed in the vessel which is surrounded by the oxygen. In vessel which is surrounded by oxygen. So these are surrounded by the oxygen. So that is how we can condense that into the liquid state. So that is how we can get the pure ozone. Now we can discuss that what will be the properties of ozone is. Because ozone is highly reactive gas, because its reactivity will be very high, and since it is right, the preparation is endothermic, and its reactivity will be very high because of its high energy, and let us check how the reactivity is very high. So let us check in gaseous state what is its color in that liquid state and in the solid state. So in gaseous state it is pale blue gas, but it is a yellowish bluish liquid, whereas solid will be violet black. So let us check that its properties is. So if we talk about the properties of that is ozone. So if I discuss the properties of ozone, I can write like this, that is pure O3 is a gas. Pure O3, when a gas is that is pale blue. Pale blue. And in liquid state it is a dark blue liquid. It is a dark blue liquid, and that is in solid state it is violet black. Whereas in solid state, so in solid state we used to say that in solid it is a violet black. So it is a violet black color solid. So it solidifies as a violet black color solids. That is about the one of the property of that is ozone. We can write that property 1. We can write that another property as, we'll say that O3 is, that is ozone is thermodynamically unstable. It is thermodynamically unstable, dynamically unstable. So we can write that this is thermodynamically unstable. O3 decomposed to give O2 plus O. It is thermodynamically unstable, so it decomposes into oxygen. Because we say that because decomposition is exothermic. So we write that exothermic. So we write that delta H is negative, delta S is positive. So I'll write that delta G is negative. Therefore, delta G is negative. It means that it is a spontaneous reaction. If it is a spontaneous reaction, then it can be used as an explosive. So thus the reaction is spontaneous. Thus the reaction we used to say that is spontaneous, and we say that spontaneous, then we'll write that if it is spontaneous, so can be used as explosives, can be used for explosives, we can say that. So that is the reason that we are going to use this for the explosive purpose, because delta H is negative, delta S is greater than 0, so and the delta G is always negative. So its reaction is always spontaneous, which can take place on its own. That is what we mean by the spontaneous reaction. So this is used as explosives. Now it is a powerful oxidizing agent. It is a powerful oxidizing agent. So powerful oxidizing agent. Oxidizing agent, we used to say that the oxidizing agent, because we used to write that as we say that if I'm having lead sulfide treated with ozone, then it can convert into the lead sulfate. The ozone, if reacts with lead sulfide, it will get converted into the lead sulfate plus O2. You can write like this, that is sulfate plus you get that O2. So we require that it is 12, so we can write that 4 is there, so 8 4O2. That is how we can write the reaction. So it is highly, that is reactive. It acts as an oxidizing agent, and we get the reaction like this. Even ozone reacts with the Ki. That is, we can write that it reacts with I, that is Ki. We'll say that if we react ozone with Ki, so Ki when reacts with ozone, it gets converted into the KOH plus O2 plus, we used to say that the iodine is liberated in this case. So that is in presence of, that is, we'll say that aqueous solution H2O. So write that it is, that is KOH is formed, I2 is formed, and the O2 is formed. That is how we can write the reaction of that Ki is. So in presence of Ki, it get converted into, that is like that, we can write the reaction, and that decomposition reaction in presence of water. The aqueous Ki is treated with ozone, it will get converted into the KOH, and iodine is liberated in that reaction. So this is explaining its oxidizing property, a very good oxidizing property of this. So that is how we can write that it is a powerful oxidizing agent. Next we can write is, that is quantitative estimation of ozone. So if I write that quantitative estimation of ozone. So if I write that quantitative estimation of ozone is, so we'll write that the quantitative estimation of ozone, we know that the quantitative estimation of ozone is treated with the Ki. Then in presence of that is water, so I'll write that when ozone is treated with Ki, O3, when treated with Ki, it will in presence of, that is, it is treated with Ki in presence of water. I got that it is, that is twice of KOH, I'll write that, plus I2 is liberated plus O2 is liberated. So I'm going to write that the reaction is like this. So it forms that this is iodine which is liberated. This iodine which is liberated is absorbed in the hypo solutions. So this I2 liberated is treated with the hypo solution Na2H2O3, that is hypo solution. We used to say that this hypo solution is going to estimate that it is going to form that Na2H4O6 plus twice of Na is formed. So we are able to estimate that what is the equivalent of oxygen which is present, equivalent of ozone which is present in the ozonizer or in the mixture. Because number of equivalents of this used will be equal to equivalents of I2 is equal to equivalents of I2 here. Then equivalents of I2 here will be equal to equivalents of ozone which is present in the mixture. So we are able to get that what is the free ozone which is present in the mixture by estimating this. And ozone is also absorbed by turpentine oil. We know that ozone is, right now we can write that here. That is, we can write a note like this. That is, the ozone is absorbed by, that is, absorbed by turpentine oil. So that is turpentine oil, that is the ozone is absorbed by the turpentine oil. So we used to write that it is absorbed by, that is turpentine oil. That is about that the estimation of ozone is, how we can estimate that what is the amount of ozone present in the mixture is with the help of this estimation reaction. So also we used to say that the other we can write that the fifth one, that is the gases like. So the gases like NO, the nitrogen oxide gases, which is right now, and right now, and other oxides of nitrogen. The other oxides of nitrogen, that is right, the gases like these and nitrogen oxide and other oxides of nitrogen emitted from the exhaust system of supersonic jets, that is exhausted from the right, exhausted from the jets in the atmosphere, supersonic jets in the atmosphere reacts with ozone. Atmosphere reacts with the ozone. Atmosphere reacts with the ozone and reacts with ozone. So they are these gases which are exhausted from the jets and the aeroplanes, right? So exhausted from these aeroplanes and the jets are depleting the react with the ozone and decreasing and depleting the concentration, depleting the layer of ozone, the layer of ozone in the atmosphere, layer of O3 in the atmosphere. So that is depletion of ozone layer. So if the ozone layer is depleted, then the UV radiation can enter into the Earth's atmosphere. If the UV radiation enters into the Earth atmosphere, then in that case, the temperature of the Earth will increase with the higher degrees, much higher than that is. So that will be very, a very severe, that will generate the severe conditions in the Earth crust for the living beings. So we'll say that the depletion of layer of ozone. So reacts with O3 and depleting the layer of ozone in the atmosphere. In the atmosphere, we say that atmosphere, we'll write that like this. So that is the depletion of atmosphere is. So we used to write like this, that is NO, which reacts with ozone to convert into NO2 plus O2. That is how the depletion of ozone layer is taking place. So that is the threat to ozone layer which is present in the atmosphere. Another threat of ozone layer is the uses of refrigerant, that is freons. The freons are also depleting the ozone layers. So we'll write that another threat. Another threat for the depletion of ozone layer is threat for the depletion of ozone layer is, so another threat to depletion of ozone layer is the use of freons. Of ozone layer is the use of freons. You know that what is freons? They are chlorofluorocarbons. Freons, they are chlorofluorocarbons, the freons which are used. So which are used in aerosol spray and as freons which are used in used as refrigerant and that is used as the aerosol spray, used and are used as and aerosol sprays. So they are depleting the ozone layer. So there is the another threat for the ozone layer is the use of freons. Freons, they are used in refrigerators or AC. So they are also, that is depleting the ozone layer is. Now if we talk about that the structure of ozone, so we can write that what is the structure of ozone is. So if we write that what is the structure of ozone is, we can write like this. That is, we can say that the structure of ozone is like this. That is structure of ozone. So its structure will be like this. That is, we can write like this. That is, you can say like this. That is double bond O, and you can write a coordinate bond like this. That is the structure of ozone is. So here we can write that, or you can also write like this. That is ozone, which is having like this. Obviously, the bond angle is like this because the two lone pairs are present on this. So the two lone pairs present on this makes this bond angle very small. It is around 112. The bond angle is around that is 112, and we used to say that this is 128 picometers. This is also 128 picometers. It means that the bond length is same and the bond angle is 112. That is. So that is 112 and no, it will be 117. So the bond angle is 117 because of sp2 hybridized, that is sp3 hybridized. It is because the two lone pairs is also present in that, because of the repulsion in the lone pairs, it increases the bond angles. So we write that, but the bond length are same in that. So hybridization is sp3 and is diamagnetic in nature. It is diamagnetic in nature because of even number of electrons. So it is diamagnetic in nature. So that is the structure of ozone is. So that is the structure of ozone. Now we can write that the chemical properties of ozone. Now we can write that what are the chemical properties of ozone is. So the chemical properties of ozone. So we can write that what are the chemical properties of ozone. These chemical properties of ozone we can discuss in the next class. So that is all about oxygen in this class. We can discuss the chemical properties of ozone in the next class, and we can also discuss that about sulfur in the next class. So that's all in this class. Next class we can discuss about the chemical properties of ozone is. So that's all in this class.